Hello and welcome to the Google DeepMind podcast with me, Professor Hannah Fry. Now, those of you who are watching will notice that we are not in the studio today, and that is because we are backstage at the AI for Science Forum, a very special event that has been co-hosted between the Royal Society and Google DeepMind. And as part of the day, I had the opportunity to speak to Demis Hassabis on stage to interview him, and we thought that you might like to hear that conversation, so we have included it here as a special episode. And then even more special than that, as though one Nobel laureate wasn't enough, we have three further Nobel laureates joining me on stage for an extended panel for you to enjoy. Okay, now, for the next session, it is always an absolute treat for me and often a mind-boggling experience to get to interview your co-host for today, Sir Demis Hassabis. Now, Demis is a computer scientist. He's an artificial intelligence researcher. He's an entrepreneur who co-founded DeepMind in 2010, where he is still CEO. Now, I don't know how much you know about Demis's background, because as well as the Nobel Prize and the knighthood and being a fellow of the Royal Society and AlphaFold and AlphaGo and having 150,000 citations, he also had a previous life as a very successful neuroscientist, chess champion and video games designer. I have to say, I have a theory that actually Demis worked out the secrets to AGI a little while ago and has been hiding it in his basement and then just like slowly eking out all of these massive breakthroughs one by one to the rest of us. But one thing is for sure, our conversations are always genuinely fascinating. So please welcome Demis to the stage. Thank you. Thank you, Demis. Thank you so much. Okay, I heard that you didn't know that the Nobel Prize was coming. Is that true?
No. Yes, no.
Really, really?
Yeah.
How did you find out?
Well, it was quite a funny story, actually, because we'd heard some rumour that AlphaFold had been put sort of nominated, but you never expect something like that. And in the morning, I was just getting on with my normal work. Actually, my wife was working at home as well. And it got to about 10:30, and we thought, oh, well, obviously, it's not happened this year because we hadn't heard. And then suddenly, my wife's computer started ringing on her Skype, I think it was. And I was like, what's that annoying noise? And then it turned out to be a call from Sweden, and they were desperately trying to get hold of my number, and they didn't have John's number either. So everyone was in a kind of panic, but it all added to the drama of the moment. Just
you had to
10 minutes
John's
before,
number.
Yes, exactly, just before it was all announced.
Absolutely amazing.
Yeah.
And I also saw that you celebrated by having a poker night with some chess champions, including Magnus Carlsen and Hikaru as well. I want to know who won. What's your bluffing strategy?
Well, it turned out, so that happened on I think it was on the Wednesday, and it turned out that there was a big, huge chess tournament going on in London, and one of my old chess friends from when I was young, was hosting a poker and chess evening the day after. So I thought it was the perfect way to celebrate. And I don't recommend a home poker game with a couple of world poker champions and a couple of ex-world chess champions if you want to win some money. But that's my idea of fun, and it was actually an amazing night. I know it sounds pretty nerdy, but it was actually my idea of heaven to
Not
celebrate it.
Sounds like
I can't tell you the bluffing strategy, otherwise I'll never beat Magnus again. Yeah.
Well, this is true.
Yeah.
This is true. Okay, so I mean, aside from the Nobel Prize, a sentence that no one has ever said, but before that, in advance of that, you also were named as a citation laureate because the AlphaFold work has now been cited over 28,000 times, which is incredible. I mean, this is really not very long ago that it came through.
Yeah.
Are there standout applications for you that really resonate?
Well, I mean, it is mind-boggling, really, and it's everything we hoped would happen by putting AlphaFold out there and open sourcing it and putting out with the community with our fantastic partners at MBOR EBI, like Janet and Ewan in the audience as well, to get it out there to everyone. And I mean, there's so many applications to mention, but I think maybe I can mention two or three of my favorites were the kind of determining the structure of the nuclear pore complex. It's one of the most important and largest proteins in the human body, and it's really important because it governs the molecules and nutrients that go in and out of your cell nucleus. And actually several teams used AlphaFold predictions as well as their own experimental data to finally piece that very, very complex protein structure together. So that was amazing. Another piece of work that I really like is Feng Zhang's work from the Broad, developing a molecular syringe to deliver sort of drug payloads to hard parts of the body to reach. And he also used AlphaFold to help modify how that molecular syringe was designed. And then maybe finally, my other favorite project is from the University of Portsmouth, John McGeehan's group, designing plastic heating enzymes using AlphaFold. But I think it's just a small sample of all the incredible work researchers are doing with it.
But these kind of projects, I mean, these are your favourites, right? The ones where it's not just the sort of the technical idea itself; it's the potential impact that it can have further downstream.
Yeah, that's right. I mean, that's why I was always intrigued by the protein folding problem or protein structure prediction problem, was because I felt we sometimes call it a DeepMind, a root node problem. What we mean by that is, if you think of the whole tree of knowledge, there are certain problems where if they're root node problems, if you unlock them, if you discover a solution to them, it would unlock a whole new branch or avenue of discovery. And I always felt that determining protein structure in this way would do that. Lead to disease understanding, drug design, and much more. And that seems to be what's happened.
Okay, so not to be greedy,
yeah.
But what's next? Is there another AlphaFold? I mean, GNOME is a personal favourite of mine. Maybe tell us a little bit about that project.
Yeah, so GNOME, look, there's so many areas, and actually James mentioned it in the morning, and Pushmeet talked about it as well, that we're touching on nearly every area of science. And GNOME is one of my favorite projects, which is on material design. And I think material design has some of the same characteristics that we look for in a problem that's suitable for AI. It's a massive combinatorial space. You need to try and build a model that understands the physics and the chemistry of the natural phenomena. And then if you have a model like that, you can then maybe use it to do a very efficient search through that search space, combinatorial space, and then find an optimal solution. And in materials, I think that would be also just as groundbreaking. You could imagine designing new batteries, or maybe one day discovering a room temperature superconductor has always been one of my dreams. And so I think we're obviously at the early stages of that. I would characterize it at sort of AlphaFold 1 level maybe, and we've got to get to AlphaFold 2 level of predictions, but we can see a clear path from there, and GNOME is the beginning of that work. We published it in, I think it was in Science last year, and we discovered 200,000 new crystals that no one had ever seen before. So I think that shows some of the potential of AI in things like material design. And then maybe the other thing I'm excited about is AI applied to mathematics, and perhaps solving one of the great conjectures, maybe one of the Millennium Prize problems, and using AI as a material as a big part of that solution.
So that idea though about GNOME, but also about AlphaFold is you're sort of shortcutting, or you're making the sort of synthetic world really serve your advantage, so that you're not having to do everything through experimentation. I know that you and Paul Nurse have been talking about a virtual cell for a long while. Tell us a little bit about that.
Well, Paul has been one of my mentors. He's very generously mentored me in the life sciences for more than 25 years now or something, and it's been incredible, sort of inspiring talking to Paul very regularly about these topics. And unusually, I think Paul is, for a life scientist, is biologist. He's thought a lot about biology as an information system. He's written a lot of interesting research papers on that. So we've always had this discussion in the background. And I've always wondered, every sort of 5 years or so, I've thought, do we have enough technologies, enough know-how to actually really attempt this Mount Everest of a problem of trying to build a virtual cell, a simulation of a cell, basically, that would be predictive of something that's really going to happen. And every 5 years I thought, we don't really have enough technologies yet. But finally now, I think the answer is yes, we probably do have enough know-how and techniques that we could attempt this seriously now. And maybe in the next 5 to 10 years, we could eventually build up a picture of a virtual cell, perhaps a yeast cell to start off with, as Paul's always been working on as the model organism for this. And my way of thinking about it is, you can think of AlphaFold 2 as essentially solving the static picture of what a protein looks like. But of course, we know biology is a dynamic system. That's where all the interesting things happen in biology. And AlphaFold 3 is our first step towards trying to model those interactions. So AlphaFold 3 can model, pairwise interactions between proteins and proteins, proteins and RNA, proteins and DNA. And then maybe the next step up from that would be to model a whole pathway. And then eventually, maybe we can make it to an entire cell.
Amazing. I mean, I imagine that the advent of quantum computing will make a difference to this, that's possible to do simulations down at the molecular level.
Yeah, so look, quantum computing is very exciting. It itself is accelerating. And James also mentioned earlier this morning about the interesting cross-pollination that's happening between AI and quantum computing. Actually, we collaborate a lot with our quantum computing group at Google, which is one of the world's best quantum computing teams on things like error correction codes and things like that. But of course, one of the uses of a quantum computer would be to simulate quantum systems like molecules and atoms and things like that and compounds, and then produce a lot of synthetic data potentially. But interestingly, I also have a slightly controversial take, which is, and I've talked to some of the world's top quantum computer scientists on this, is that actually I believe that classical Turing machines, classical computers, are capable of a lot more than we previously thought. And I think that's what the work that we've been doing has showed, both with AlphaFold, but also previously with AlphaGo, our program that beat the world champion at the game of Go, which, just as an indication of the complexity of Go, much more complicated than chess, and has more possible board positions than there are atoms in the universe, 10 to the power 170. So what that means is you can't possibly brute force a solution to find the best move in a particular position. You have to do something much cleverer. And so both protein folding also has enormous amounts of possibilities if you were to do it naively and just try every combination, which is the naive way of doing it. But yet, if you do things like you do a huge amount of pre-compute to build a model of the system before you ask it the question that you're interested in, what move should I play in this Go position? How does this novel protein fold? It turns out you can actually come back with a near optimal move in Go in a few seconds, or fold a protein in a matter of minutes, which you might have expected in protein space, at least, that you might need a quantum computer for or quantum algorithm for, and it turns out you don't. So I actually think we should take this very seriously, that classical systems, if you use them in the right way, may be capable of modeling a lot more complex systems, perhaps even counterintuitively quantum systems, because normally you talk about needing quantum computers to model any kind of classical system, but it may be that classical systems can model quantum systems. And I've tested this out with some of the people like Professor Zeilinger, who won the Nobel Prize in Physics recently for his pioneering quantum computing work, and he thought it was very interesting. And David Deutsch, also one of my scientific heroes, who's basically invented quantum computing, said it was crazy, but the right sort of crazy, which, coming from him, I take as a compliment and as also a sign to maybe pursue it further.
So let me make sure I understand this then. So I guess the classical computers sort of thought of as deterministic machines, and you're talking here about probabilistic questions, but you can use the deterministic ones to answer
and the idea is, the quantum systems, anything you try to model, any natural phenomena, if you start trying to model it by every possibility that it could take, that system, then you quickly run out of computation in a classical system. You need too many bits to model it. But that's just not the way that you would attempt to do it with a classical system. You would build a model first that learns, my conjecture on it would be that any natural phenomena tends to have structure, and if it has structure, you could potentially learn it with a classical machine learning system, learn an efficient model of that, and then use that to search the possibilities in an efficient way. So I think that might get around some of the inefficiencies from a naive way of doing this. So I mean, it's a pretty big claim. So I'm making it in a soft way, but it's a kind of hobby of mine to look at this area, and it's something I think that could be quite promising.
Another hobby of yours that has now spun off into its own business of isomorphic, because I mean this is work using AlphaFold to apply to drug discovery.
Yes.
You've got some pretty prestigious partnerships now as well. Can you tell us what isomorphic is focusing on at the moment?
Yeah, so isomorphic is our spin out to try and revolutionize drug discovery from first principles using AI as a sort of from the ground up, trying to reimagine the drug discovery process. And I had this in mind when we were doing AlphaFold. So I think it's one of the most obviously good use cases of AI is to cure diseases. I mean, what better use of AI could there be? And so that has always been one of the number one things I wanted to do with AI once it got mature enough. And so AlphaFold, of course, is a great tool for fundamental research and fundamental biology research. You know, over 2 million researchers around the world have used AlphaFold and the structures we put out there. But it's also a practical use to help with drug discovery. Of course, knowing the structure of a protein is only one small part of the whole drug discovery process. And so we spun out isomorphic after we did AlphaFold 2 to build on that work and extend and build new machine learning systems into adjacent areas. Things like designing chemical compounds and drug compounds, testing for toxicity and predicting things like ADME properties, important properties that you need for drugs to work in the body and minimize side effects and things like that. And we're building, you can think of as building up further AlphaFold-like models in these adjacent areas. And then eventually we'll stick them all together. And we hope that, one day in the near future, actually, we'll reduce the time down from years, maybe even decade, to design a drug down to months or perhaps even weeks. And that would revolutionize, I think, the drug discovery process.
This really does seem like one of those endeavors where you're not having to make a choice between doing something that benefits humanity and doing something that can be profitable and sustain itself. How much do you look for those kind of projects at the outset, or how much of it is that you do sort of blue sky research and then hope that it'll turn out that way in the end?
I think we do both. So we follow, we're research led as a group, so always have been. So we try to do what's the right next step for researching, AGI, artificial general intelligence, or something like AlphaFold, where you really want to solve the scientific challenge. But then in the back of my mind, I'm also pretty practical. So I want to solve things that will also have a practical, positive impact on the world pretty directly. And so if you can find projects that do both, then that's, the holy grail really, and something that really worthwhile investing a lot of time and effort. And AlphaFold was exactly like that. So I was fascinated by the problem itself. As Janet mentioned earlier, the more you get into proteins, they're exquisite nano machines. I mean, they're unbelievably beautiful. I totally agree with Janet on that. And you sort of fall in love with them when you start working on them. And it's just unbelievable what nature's engineered. But then, I always had in mind that that would be a social good, but then isomorphic can do both, right? I think we can, cure many diseases with the help of AI, but also it should be an incredibly valuable company. And that, of course, if that turns out to be the case, that will give us more money to invest in fundamental research. So it's all a virtuous cycle.
With all of these different projects going on in fundamental research, I mean, do you think that we are at this moment where we're going to have a sort of a vertical takeoff, as it were, on progress?
I think we are on the cusp of that. I really do feel like we're on the brink of a new golden era of discovery, like the whole of today's symposium is called. And I think what we need is a lot more interdisciplinary science. So using AI, bringing it in the right way, asking the right questions with domain experts. And I think it's almost limitless what its applications could be. And of course, AI itself is a scientific discipline, is improving all the time. So there's applying today's technologies directly to the other fields. And then there's also continuing to improve AI itself. And that as well is a sort of exponential improvement. So, there's a lot of, I think, progress to be made in just the next few years.
I think interdisciplinarity has definitely been one of the big themes of today. But I think that the other themes are about what science looks like in the future. What does it mean to do science in an era of AI? And I know that you're a sort of big advocate for the scientific method. But just talk to me a little bit about that. What does that look like as we kind of move forwards?
Well, look, I think the scientific method is arguably maybe the greatest idea humans have ever had. I think underpins obviously all of science, but then also because of that, science and technology, modern civilization. And I think more than ever, we need to anchor around that method in today's world. And I think especially with something as powerful and potentially transformative as AI, I think it's important we use more the scientific method than perhaps lean on normal sort of technology A/B testing out in the wild that is often the case with new technologies. And I feel we should treat this more as a scientific endeavor if possible, although it obviously has all the implications that breakthrough technologies normally have in terms of the speed of adoption and the speed of change. So it's an interesting situation that we're in. And I think we need to use the scientific method to do things like better understand what these systems do, build benchmarks and rigorous evaluations for understanding the limits of the capabilities, interpretability. Actually, I think we should be using neuroscience techniques which obviously built for understanding real brains to model virtual brains. I sometimes call it virtual brain analysis. What's the equivalent of an fMRI of these neural networks, right? And I think there's a lot we can learn and bring across and translate from the natural sciences to what is basically an engineering science. I call it an engineering science because unlike the natural sciences, you have to build the artifact of interest first, and then once you have it, you can then use the scientific method to reduce it down and understand its components. So it's a hard challenge, that's for sure. And these systems are, in my opinion, are as complex as the natural phenomena we normally want to study. So no one should think that it will be easier to understand one of these artificial systems than it would be to understand a natural system. I think they're just as complex in many ways. So we've got a lot of work in front of us, and I think this is something that industry, academia, and civil society needs to come together to understand better, and including how to deploy these technologies.
Where does a scientist's intuition fit in all of this?
Well, I think scientists' intuition and creativity is critical. I think right now the AI systems are just tools. I think they're great for finding correlations and patterns and structures in data. But for the moment, they're not able to come up with their own hypotheses or their own questions. And I think, as all the scientists in the room know, I think that's the hardest thing about science, is asking the right question. And that has to still come from human scientists. And for the foreseeable future, I think that will be the case. So I think it could be, that's why I'm very excited about the use of these AI systems as maybe the ultimate tools to help us accelerate scientific discovery.
I guess on that topic of humans, I mean, there has been some recent research saying that the progress of scientific discovery has slowed down over recent years. What's your take on that, and what could be done to change that?
Well, look, I think things, I've seen studies like that too, and I think there's interesting conjectures as to why that is. Science has become bigger endeavor. You need to have bigger teams, more expensive equipment, and so on. So that leads to some slowdown. And perhaps the questions we're now tackling are ever more complex. So that's also tricky. I think what I'd recommend is, again, I think a lot of the advances in the next 10 years are going to be interdisciplinary work, but sort of, bringing together experts from two or more fields, and then that making the big advances in between those areas. And actually, that's the story of DeepMind, which originally I think was a combination of neuroscience ideas with machine learning ideas. It's also the story of AlphaFold, which is a combination of biologists and chemists on our team, along with machine learning experts and engineers. So I've always found that's the place to get the most advances most quickly. And actually, we're announcing today, $20 million fund from Google.org to kind of fund this kind of interdisciplinary work in academia. And I hope that other funders, join that effort. And I think that's what we need, is to train a new generation of PhDs and postdocs in these kind of combination of these different areas.
What an extraordinary piece of news to finish on. $20 million for research in interdisciplinary teams. Demis, thank you so much indeed. Thank you very much, Demis.
Great.
Okay, I think, Demis, if you go down to join the other laureates while we sort out the stage. Now, I should tell you, actually, the laureates, the word laureate, by the way, comes from the laurel wreath, which was given to victors in ancient Greece as a sign of honour. And every year, there are 5 separate prizes that are awarded to those who are considered to have conferred the greatest benefit to humankind, courtesy of Alfred Nobel. There is a rumour that there is no Nobel Prize for mathematics because Alfred Nobel's great love ran away with a mathematician. Have you heard this? I mean, we are charming. What can I say? Now, so joining me on the stage, we have 3 further recipients of this esteemed prize. John Jumper. We've not yet had the pleasure of having John Jumper on the stage thus far. He is a director at Google DeepMind, where he led the team that built AlphaFold and continues to work on new methods to apply machine learning to protein biology. John has won numerous awards for his work, including the Lasker Award, the Breakthrough Prize in Life Sciences, the Canada International Award, and of course this year's Nobel Prize in Chemistry. We are also joined by Sir Paul Nurse, who is CEO of the Francis Crick Institute and winner of the 2001 Prize in Physiology of Medicine, for his work also on proteins, specifically the protein molecules that control the division of cells in the cell cycle. And finally, Jennifer Doudna, who earlier shared her lessons from CRISPR with James. She won the Nobel Prize in Chemistry in 2020. Please join me in welcoming our 4 Nobel laureates to the stage. Thank you. Okay, so I know that often you get asked about where were you when you heard, what were you doing when you heard. I want to ask you a slightly different question. I want to ask you about whether there was a moment when you realised that the work that you were doing was genuinely groundbreaking. Was there sort of a moment when you realised the significance of it? John?
I think there were kind of 2 moments for me. One was actually like watching Twitter after, whenever you release some work into the world, you anxiously refresh Twitter and, we'd stick the word AlphaFold and just see what tweets popped up. And I remember seeing so many, when the database became available, so many astounded grad students saying, I think one was, how did they get my structure? It hasn't been published, right? How in the world? And just had absolute astounding, the number of people that said either, that we predicted their structure, this person down the hall, we predicted their structure. So I thought they were absolutely blown away. And I think the second moment was there was a special issue of Science related to the structure of the nuclear pore, the largest collection of proteins in the human cell, protein chains. And there'd been 4 papers in a special issue of Science, and 3 out of the 4 had made huge usage of AlphaFold, something like more than 100 mentions of the word AlphaFold in Science, and we had nothing to do with it. We didn't know it was happening. It just appeared one day, and that was the moment when I really knew that people were doing, science worthy of appearing in Science, right? One of the most prestigious journals in the world, on top of our tools and without us. And the moment at which people start, making these discoveries on top of what we've built, that's when you really make it as someone who makes tools.
Jennifer, did you have a moment?
Well, I think for us, maybe also two moments. One was in the fall of probably 2011, when we had started a collaboration with Emmanuel Charpentier to work on CRISPR, which is a bacterial immune system, and we wondered, how does it work? And we had together figured out that it's an RNA-guided system that targets DNA for cutting, for cleavage, and furthermore, that we could actually program the system because we understood the chemistry of how it worked. And it was really one of those aha moments of, I personally, I was just astounded that bacteria had figured out how to do this, and that furthermore, we now understood how to harness that system to manipulate DNA in new ways. So that was one. And then the second one was sort of akin to what you said, John, where I think it was then fast forwarding about a year. So we published that work in the summer of 2012. And by the fall, I was starting to get emails from people all over the world who had read the paper and said, oh my gosh, this is so exciting. I'm now using it to test genes in Drosophila. I'm starting to test genes in zebrafish. I'm excited about what I'm doing in human cells. I was getting messages from people that I often barely knew who were just very, very excited. And you could start to feel the momentum that was building in the field.
Paul.
Well, I'm the oldie here, so it's 1985, I'm afraid. And I work on yeast, as you've already been told. And my lab had worked out the genes that controlled the cell cycle. That is the process that leads to the reproduction of one cell into two, fundamental to growth and development in all living organisms. And we'd identified that gene, but the blunt thing is that who cares about yeast? I mean, being perfectly honest, I care about yeast, but most of the world does not care about yeast. And so I found our work wasn't really being taken much notice of, and so thought, do humans have the same gene? Now, this is long before the human genome sequence and so on. So we did a crazy experiment. I want to just tell you how crazy it was. We had a mutant in yeast that couldn't grow because it was defective in this gene. We took the first human cDNA library, it's genes that had ever been made. We didn't make it, we got it a few months afterwards, and fundamentally sprinkled the genes onto the defective yeast, arguing that if there was a gene in humans that could do the same job as the defective gene in yeast, if the yeast cell took it up, if it could be expressed, if it worked, then those cells would grow and divide, and we could get the gene back and show that humans had it. That experiment had no right to work. Yeast and humans probably diverged 1,500 million years ago, and we were demanding that it still worked after 1,500 million years, and you know, it did work. When we got that result, and by the way, there were a couple of months when we had to sequence the genes, it took that long then, I used to think, I'm just going to go home and believe this works. Tomorrow I will go into work and we will have shown it didn't work. But it did work, and that's when I thought perhaps it might be recognised, because it wasn't yeast, it was humans.
What an amazing collection of stories. Now, I know that all of you must be bursting with questions for our panel. So I might take some questions from the audience. Do we have mics running around? Oh, there's one there. I might take them in a little cluster. Is there anyone else who would like to pop them in? Okay, so we have one here, another one here as well. Roger.
It's been such an impressive day, and thank you for closing it out like this. I've got a very playful question, which is if you could take yourself back in time and met your 18-year-old or your 21-year-old self, and you could say something that would reassure that person that you were making good life choices, what would you say? And you're not allowed to say you're going to win a Nobel Prize, all right? That is, or anything to do with that. So what would you say to your 18-year-old, 20-year-old former self?
Okay. Well, we'll collect another question. I think Roger Highfield just here had a question too.
Roger Highfield, the Science Museum. Just a comment. We've seen images of Sycamore, the very cool-looking Google quantum computer. Can we please get some sexy-looking AI hardware that we can collect to the Science Museum, please? But actually, a more serious point is, and you've kind of alluded to it, Demis, is this thing about how AI is great at giving you answers, but it's not very good at giving you mechanistic insights. You've got billions of parameters. They've got no physical meaning. How much of a barrier is this to the public trusting AI? And I talked to John about this as well. Where are we in actually getting an AI that can give us the laws of biology, just like we've got the laws of physics, so we can get true mechanistic insights?
Fantastic. Two very good questions there. We'll start with the first one. Demis, if we go to you first, what would you say to your 18-year-old self?
Well, it's a little bit complicated for me. I mean, I did actually have this plan when I was 18. So what is amazing is it worked out. But what I would have told myself, maybe it was the chess player in me, as I always plan like many, many years ahead. But that's what happens if you play chess from the age of 4. You end up like this. But you probably what I would have said to myself is just enjoy the journey a bit more, because it will like work out. Like, because at the time it's like, how is this ever going to work out? I had all these dreams, and then that's probably what I'd recommend to my 18-year-old self.
Tom?
I think two things, actually. Amusingly, I was thinking, don't worry, Carolyn will marry you. But it's the gradient descent of life. Do the right thing right now has worked out really well, and like be open to the interesting things that will open up for you. And then I think we're in, one of the golden ages of biology and AI and biology, and it's really fun to live through that. And so I think like, don't be afraid to be locally optimal. Just basically the opposite of Demis's advice.
Are you a gradient descent, or are you planning strategically in advance?
Probably closer to John. Yeah, I think I would tell my 18-year-old self to follow my passion and never, ever give up. And don't listen to people that are naysayers. That's really important.
I came from a non-academic background. I couldn't believe that you could get paid for just following your curiosity. I still don't believe it now, 40 years later, 50 years later. Actually, more than that, 55 years later.
Just hold on to believing that we can, okay, as president of the Royal Society. You could. The second question from Roger there, about intuition from AI systems. Demis,
yeah, look, I think actually this is pretty interesting. I'm not so worried about it as other people are, because I think we're in a moment in time. So what I said earlier, actually, in my talk was what I believe, which is that AI is an engineering science. So what it means is you have to build the artifact first, worthy of study, and then you can break it down with a scientific method. And so what you've seen in the last 5-10 years is the building of the artifacts that are even worth putting any effort into study, until you had things like today's, transformer models and AlphaFolds, AlphaGos. The earlier systems were probably not worth really putting the effort into study because they were not sophisticated enough. Now they are. So now people are seriously studying the current systems. On top of that, you've got the additional benefit of these systems improving themselves, and you're at the minimum, I think we'll be in a situation where, firstly, the systems might be able to explain themselves in language or mathematics or code. So we're getting close to that. So you could sort of say to a system, okay, you've understood this. Now, explain that in a mathematical equation to the extent that it can be. And I'm not sure biology can be explained like the laws of physics, by the way. I think it is a lot messier. It's more to do with interaction. So I think a simulation would be more appropriate that you probe than like Newton's, laws of motion or something like that. I don't think biology can be reduced to that. It's too complex. And then the other thing is, what I also said earlier about applying neuroscience techniques, analysis techniques to these artificial neural networks, and we should be able to get at least the same level of insights into them as we do with natural brains. So if you combine that together, we should get pretty far already, let alone with further engineering efforts that we're going to put on top to decompose these systems. So I think in the next 5 years, we'll be out of this era that we're currently in of kind of black boxes.
Fascinating. Okay, further questions. All right, we've got a couple here, so let's go 1, 2, and then if you can keep your hands up actually so I can see. We'll go 1, 2, and then we'll go over there. We'll read them out in chunks if that's okay. Go for it.
Thank you. Denny Newman-Griffiths from University of Sheffield. Just following up on the topic earlier came up of the social sciences in AI. And the idea was raised about potential for AI to transform social sciences. I want to ask you about flipping that around and thinking about, in your understanding, how can you see the work of social sciences helping to transform these next futures of AI? Mm-hmm. And, building the ways to kind of transform that engineering science into the interdisciplinarity that we've been talking about, where AI tools are being combined with really deep understanding of application areas and contexts. Fascinating question.
Your neighbor next to you.
A very simple question. Is attention still all we need?
Thank you.
Michael Chang from the National Eye Institute in the U.S. Thank you very much. This was an awesome conference. I have the theme here is AI to do better science. And I think one of the common things that we do is, we can just teach scientists more about AI and they can use it. My question is flipping that around. Do you think there are things that AIs do not do that scientists should be getting more training on to maximize their added value, and what those would be? Just love your perspectives on that.
Fascinating. Okay, all right, so we'll start off with, I might start with you, Paul, actually, because you were the one who was talking about social sciences earlier. So, AI and social sciences, how much do we have to think about that sort of interface between humans and the machines?
Well, first of all, I think we need to focus more on the social sciences to help us scientists. We have to appreciate, though, that this is pretty complicated, the human interactions. And so I'm not sure how much it's going to help us at the beginning. Not sure about that. But we really ought to be accommodating it, ought to be thinking about how it might. I could sort of imagine certain social sciences problems, and I suspect you're a social scientist, to do with transport and things of this sort. So I think there are some mechanical things trying to understand how human beings interact and work. Well, you have to ask Carol, was it?
Yes, sure.
No.
So John, yes,
Was it
exactly.
Carol? Yes.
Oh, Caroline.
Caroline, yes.
Yes, that's Carol.
Yes.
In other words, sorry, I thought it was straightforward. Getting emotion, understanding emotion is going to be difficult. Okay.
And he was looking at me. It was doubly confusing. Yeah.
Over to you, John.
I mean, should I answer this or should I go to the?
Yeah, go to the attention. Go to the attention.
I think attention is all you need. Is an oversimplification. I think one of the things that's really interesting is AlphaFold isn't just like grab a transformer off the shelf from the transformer store and apply it to protein structure prediction. You know, it took a couple years because there's a lot of work. There's a lot of new ideas where attentions is a component. But we have what we could call evoformer. We have new ideas on top. We have all sorts of, Demis runs an incredible AI research org, which goes into work every day and doesn't just say, well, we've got all we need. There's attention, right? We all are doing this work. And it's really, I think, people underestimate how much really novel and exciting work is going on in AI right now that are making these systems transformatively better, both unlocking new data sources and learning a lot more from the existing data sources. AlphaFold is the story of having the same data as everyone else and learning a tremendously more about protein structure from it. And so I think we'll continue to see these dividends from AI research. We're going to continue to see exciting new things, and we may always call something attention, but it reminds me of this old computer scientist joke. I don't know what the scientific computing language of the future will look like, but it will be called Fortran, right? And so we tend to keep the labels of ideas and then update within it. And I think we shouldn't underestimate how much really wonderful and exciting and clever research is going on these days.
Maybe I can just add quickly to that. I agree with that. And actually, the transformer architecture, which is what was invented with that paper, is been amazing, and I think will underpin be one of the main components of a future AGI system. But my prediction is it's not going to be enough on its own. I think we're going to need a couple of other big breakthroughs like that in addition, and they're still to come.
Jennifer, I might come to you just to pick up on our third question there about the gaps in what AI can do, and we need to really focus on the skill set from humans.
Yeah, and thanks for that question, Michael. So I guess what I've been thinking about with regard to that is there's been a lot of mention today about data and the kind of data that are necessary for training models like this. And one of the challenges in biology, of course, is the quality of data, but it's also the quantity of data and the fact that typically one needs a lot of data that's of high quality to train models, at least currently. And so what I'd like to see AI do for us scientists is to educate us about how to collect data, perhaps sparsely, but smartly, so that your sparse data is broad enough that it actually does provide the right platform for training. And I think that's something we don't, at least as an experimentalist right now, we don't think about that when we design experiments, but we could.
I guess that kind of comes back to the asking the right questions thing that we were talking about.
It does.
What is the best sparse data?
That's one of the key questions.
Yeah. Okay, we probably have time for another. Right, we've got in the red jumper at the back. You can go be number one, and then I need to think strategically about microphones. Okay, if we go, there's a little cluster over here, so we'll go 2, 3, 4. Further back. Ooh, yes. Just, there we go, we found it. Okay, go for it. Number one.
Hi, it's Wendy Hall, University of Southampton. Someone who's been working with social scientists for a long time, the big issue there, collecting the data and the issues around privacy, and it makes it so much harder than the sort of science you're doing. The more we can do of that, the better. My question, though, as someone who's just been suffering from a cold, as many people, please can AI sort out the common cold?
Guys, what have you been doing? Okay, we've got three very closely together here. Yeah, go ahead.
Hi, Thomas Crampton. There's been a lot of talk, obviously, about great science, a lot of fantastic science discussed. What about the people outside of this room, though, who don't understand science and might be suspicious of it. How much concern do you have that society might reject a lot of these great breakthroughs that are coming to the world, and what do you think we should do to address that?
Great question. Next to you, yeah.
I'm Wilfred Ndifon from the African Institute for Mathematical Sciences. So thanks very much for a wonderful discussion. I have two questions, if you permit. The first is that when people talk about AGI, I think a common assumption is that the target is the human intelligence. But human intelligence may be suboptimal because this is the result of an historically contingent evolutionary process. So to what extent do you think AGI is going to be something supra-optimal with respect to human intelligence? The second is about inclusion. Africa by 2050 would have the largest population of young adults in the world. This population would be serving the world. It will have to in order for humanity to continue its ascent. To what extent is the community ensuring that Africans are included? I should mention that Google has been amazing, and Google DeepMind has been an amazing supporter of capacity building for young Africans in AI. As a whole, what else is the community doing? Thank you.
Great. And then I think there's one bit immediately behind you as well. Thank you.
Thank you. Suze Kundu, Digital Science. I'm a recovering academic, a nanochemist by training. And in chemistry, technological developments in things like microscopy have always opened doors to many, many other areas of research. AI is very much the same, but I think we've seen from a lot of the speakers and the discussions today that a lot of the developments come about through industry rather than academia. So, Paul, I know you talked about research cultures and how maybe, some of our other speakers talked about how maybe the way that we reward successful research at the moment isn't conducive to making space for innovations in the same way. How do we change a global culture when nobody wants to be the first to do that? Because they may be losing out.
Okay, right, 4 extremely good questions. We have precisely 4 minutes to answer them, everybody, okay? All right, so Paul, we'll start with you. Why isn't there a cure for the common cold yet?
Well, it's difficult, isn't it? I'll go to the...
Of course, you absolutely can.
Keeping the public on board. This is really critical. It's crucial. We really need to concentrate on it. It is, of course, not the first time. Nearly always when there's been a new technology and changes, there has been concern. And I think I mentioned it earlier, we have to talk to the right people. We have to talk to the public. And too often these discussions get hijacked by interest groups and people who say they talk for the public, when they talk often for their own particular interests or their own particular passion that they have. So we have to work out ways in which we can discuss with the public and discuss in a sensible way. And I mentioned deliberative democracy. It's expensive to do, but I think it's a really important thing to do. Because bluntly, if you don't take the public with you, we won't be able to see all the merits that can come out of this. Merits in terms of understanding the world better around us, merits in terms of actually using those discoveries for the public good. We have to engage and we have to convince the public these things are right.
I think I want to actually just add on a little bit to Suze's question there, which I think also incorporates part of your question, because for all of you, we were talking a lot today about measures of success and incentives for scientists, and of course, all of you have the ultimate prize of being Nobel laureates. How has your view of success changed, and how should we kind of influence future generations across the world of scientists to make sure that we're getting the right outcomes? John, do you want to go first?
I think one of the things that's really been informing me over my scientific career is just the power and the fun of working on a team doing science. And I was able to do it at Google DeepMind. I did it for a time before my PhD. And in the PhDs are a little bit lonelier, right? You're working on a particular individual thing. And I think really the power of working within a team is really, really important. I think that provides also its own motivation. Science is about, loads of failure and occasional dramatic success, and we're all up here, right, from those dramatic successes. But I think that, and maybe Demis has it down to a repeatable science, but I think that really, encouraging people to work in teams, work together, and I think that helps provide the kind of motivation that leads to better science, that leads to more fun science. If you don't have fun doing it, you won't do it. And all the great scientists seem to be having fun at it.
Jennifer.
Couldn't agree more. And I have to say that when I think back on my career so far, I really feel great joy and pride in the students that I've trained and the work that they're now doing. And it's just, there's something incredibly satisfying about that. And actually, can I speak to one of the other questions? So, you asked about the question about Africa and involving African scientists and, young people who want to do science. So I'm really proud that the Innovative Genomics Institute has an ongoing effort right now in Kenya, where I think we've done 3 years running, we've sent a team to different parts of Kenya where they've been working with scientists there to work with them and really help them understand CRISPR. And it's really been really motivating to see some of the videos that come back where these local scientists then go back to their communities and they work with students and they get excited and they start doing interesting creative science, in their own laboratories. So I'd like to see more of that. I think there's an extraordinary opportunity there, and I'm also very excited about the things that I hear about Google doing. So I think there's a big opportunity for all of us to work together on that.
More and more people being paid to follow their curiosity, Paul.
You almost said what I was going to say.
Oh, sorry.
But I'll amplify it slightly. We live in this world of big data. And sometimes we have low standards that it's enough just to report lots of big data. There are certain journals, very high-profile journals, that seem to do nothing but actually report lots and lots of data. And I think it's worth giving some attention to creativity in the world of big data, because creativity can get lost in this scenario, when in fact there is enormous opportunities with big data if we actually take a creative approach. And we need to think a bit, what is exactly creativity? And I could go on about that, but I won't, because it's near the end. But we need to encourage in our colleagues, in our students, creative thinking. And that is a bit different from collecting lots and lots of data. But lots and lots of data really will deliver if they take a creative approach to it.
Demis.
Well, so many things to pick up on, and there's not much time. But I mean, we would, creativity would be a very interesting thing to have a whole panel discussion on it. Maybe next time we do this. But maybe just to pick up on a couple of questions. I think for in terms of encouraging the next generation, for me, one of my heroes was Feynman, but it wasn't just his physics books, which were very famous, right? But actually, it was his lay person's books that inspired me to get into science. And I really think all school kids should read them. So surely you're joking, Mr. Feynman, and the great joy in finding things out. Because I think those books, more than any other I've read, and maybe there are others like that, show how exhilarating it is to be at the frontier of knowledge and what that means. I'm feeling getting goosebumps even just talking about that. And it instilled that in me when I was, I can't remember what age, like 10 or 11 or something. And I think it would be great for school kids to be exposed to that, how incredible and fun doing science should be. And I think Feynman was one of those people who had a lot of fun doing his incredible science, and as a great role model for that.
Thank you very much to all of you. Very much indeed. Thank you. Well, as always with Demis, there was a dizzying array of topics that were covered there. We had room temperature superconductors, we had nuclear pore complex, we had molecular syringes, there was plastic eating enzymes, drug design, even poker bluffing strategies. But I think for me, the most standout moment from the conversation today is about what it means to be a scientist in the era of artificial intelligence. Because, this event was co-hosted by the Royal Society. The Royal Society, which was founded during the era of great lone geniuses, standing on the shoulders of giants, as the phrase goes. But I think that maybe we need to start accepting that those days of lone geniuses really are behind us. Because I think if we are going to address the biggest challenges that society faces, climate change, energy, disease, our understanding of the universe, then what we really need is big, talented teams of scientists who are working across traditional discipline boundaries. You know, politics has never needed science more, but I think neither has the world. And I think we need this collaboration between our public institutions, between governments, our healthcare providers, and also the private sector. Because innovation is a pursuit for people, but also by people. You've been listening to Google DeepMind, the podcast, with me, Professor Hannah Fry. If you enjoyed that episode, do subscribe to our YouTube channel. You can also find us on your favourite podcast platform. And we have got plenty more episodes on a whole range of topics to come. So do check those out too. See you next time.